Good afternoon, everyone, and welcome to the EOL seminar series. It is my pleasure to welcome Frederick Iat Hin Tam, a PhD student from the University of Lausanne in Switzerland. Frederick is in the Dawn Research Group at the University of Lausanne with a background in meteorology, remote sensing, and high-resolution weather modeling. Frederick's interest in severe weather systems stem from chasing tornadoes in the U.S. Great Plains during his undergrad studies at the National Taiwan University. During his master's at NTU, he worked on identifying dual polarimetric signatures that may be used to identify precipitation hotspots in nocturnal mesoscale convective systems. His current research interests focus on discovering new physics approaches in atmospheric science using data-driven methodologies and machine learning to improve the prediction skills of existing weather models. In his PhD work, Frederick developed a transparent pattern discovery method to find patterns useful in predicting the formation of tropical cyclones and took part in developing a causal feature selection method that can potentially improve the skills of existing statistical tropical cyclone intensity models. And machine learning applications in forecast modeling, particularly in tropical cyclone formation and intensification, is the main topic of his seminar today. For those participating virtually, welcome. You can ask your question at the Slido screen at the bottom of the presentation screen, and then we're going to be saving those for the Q&A portion of after the speaker's presentation. So without further ado, Frederick, welcome to NCAR, and the stage is yours.
Just a little bit of testing to see if everything works. Yes, everything works. So, hi, I'm Frederick. I'm a PhD candidate from the University of Lausanne. So today I'm going to talk a little bit about how to use machine learning methods to handle simulation data or reanalysis data with the goal of using those methods to discover new knowledge in tropical meteorology. So this is a thing that our group has been thinking about, has been talking about for a very long time, for the last 2 years. In my own research, I've been focusing on pattern extraction, answer quantification, and causality. So before that, I'd like to acknowledge our co-authors, my advisor in Switzerland, Tom Buchler, has been very helpful in every way, and my collaborator as well, James Rupert from OU, and some other people from my own institute from Germany, and also over at CERA. So I have received an email saying that maybe some people are not very familiar with machine learning. So I would say that actually machine learning isn't that fancy or complicated. It's just kind of very similar to what you expect from a linear regression model. So you would have some input that you may want into the model. It can be like atmospheric conditions like humidity or temperature, some other stuff. And you have an output layer. Output would be the thing that you want in your model to predict. For example, in my own research, I've been focusing on the intensification of tropical cyclones. So here you would have a lot of different nodes, as we call it. So actually there is also some arrows. So the arrow between this input and this node is actually an equation. It can be a linear equation, it can be a nonlinear equation. So the idea is just to combine all of this together to find the relationship between the inputs and the outputs. The idea is that a very simple linear regression may not be powerful enough to explain the scientific problem, but if we increase the complexity, put all of them together, maybe it's more possible to do that. So recently, in the past 2 years, there has been a lot of claims about we don't need physics in terms of the weather prediction. We can directly use machine learning to do that. And there has been some claims that those type of models can beat the existing numerical weather prediction model. This is an example in the Pangu weather paper. Basically, what they're saying is that using the Pangu weather forecast, which is wet here, it is closer to the truth of this particular tropical cyclone than the ECMW weather predictions. So, however, I think I'm not terribly convinced about this argument as of yet. One thing that I need to be more convinced about is that there is some lacking in terms of the emphasis of those papers. So to show that, I actually took the abstract of those papers and create a word cloud just to seeing what the authors of those papers are emphasizing while they're writing the paper. So you can see a lot of keywords about forecast, prediction, performance, and accuracy. This is reasonable because what they plan to do is to claim that their prediction model can beat the existing weather prediction models. However, I think one thing that's missing from this word cloud would be the trustworthiness, meaning that can we understand what the model is doing while it's making the prediction, whether it's a black box or a white box. And on the other hand, can we use this type of method to perform some scientific understanding to discover new knowledge about the Earth system? I think those are not included, or at least absent from the abstracts. So I think those two are what I'm focusing on in my own projects. So I think the two are actually related. So if we can create a model that we can trust, and then we make sure that those scientific discovery, if we see them, can be reasonable, and if it confirms to our physical understanding of the Earth system. And if we can establish it is possible to use machine learning to do such things, and it would, on the other hand, it would increase the trustworthiness as well, because other people would be like more convinced that those two is usable in atmospheric science context. So in my own case, I've been working 2 projects on this particular topic. One is using causality, causal feature selection, to optimize existing TC intensification models, statistical models that is operating by zero in-house. There's a ship's model, basically. The idea is to use this sort of feature selection to constrain those existing models and make them better, basically. And the other would be using machine learning to get new physical insight. This is a collaboration with James Rupert at OU. We are trying to discover new patterns of radiation, long-wave radiation. The idea of those patterns would be to link them to the predictability of tropical cyclogenesis. So in terms of the first project, this is a collaboration with one of former postdoc in the group, Shananya Ganesha Studish, and myself. This paper is published in Environmental Data Science, so you can access this paper with this QR code. The idea is to refine existing operational statistical TC models with ML. One thing that is worthwhile to note is that feature selection is very useful and very needed in terms of building statistical forecast models. So you might consider a situation where, for example, you start from an Era 5 data, you have tons of variables to choose from, and maybe you want to directly use all of them to predict tropical cyclone intensity. This can be doable, but it will have a large problem of overfitting. Overfitting is a term in machine learning validation, meaning that if you use this model to predict the cyclone that you use it to train the model, it's called training set, and yeah, it will perform very good because basically you learn everything there is to learn about the training data in the very complex model. However, if you use that exact model to predict other storms that it hasn't seen before during training, which we call test set, and this is very likely a situation where a model would perform poorly. So this is a situation where we call overfitting. The problem is that it learned too much about those existing storms, and it doesn't take into account that something shouldn't be there, basically. And if you try to do a little bit of selection beforehand, just to retain some important environmental condition, and you use that instead to create another model, and it might have the situation where it will perform better on the training set, on the test set, basically because it only have the information that guides the intensification of most TCs. So using that, it will be able to bump up the performance over the unseen data a little bit. So the problem that we have is that how do we do this pre-selection? So One thing that we might want to do is maybe correlation analysis. So maybe what we'll do is we have all the features that we want, we have our target, and then we do correlation analysis, and then we rank them one by one, and then we choose some threshold, say like 50%, upper 50% we keep, lower 50% we throw out. And this can be doable, but I think it has some problematic aspects. Presumably because there can be latent confounder. To explain this concept, like today, outside we have a lot of sun. And a situation like this, you might want to get some ice cream or get some soda, for example. And if you're like me, you always forget a sunscreen. And if you stand in the sun too long, you will have sunburns. So if you gather some data in the wild, and you get some information about ice cream sales, and sunburns, and there will be a correlation between the two. However, in a statistical modeling sense, it does not make sense to predict sunburns from ice cream sales. It doesn't make sense because it doesn't have a relationship between them. It's just correlation. So in terms of technical terms, this thing can be described as the spurious correlations, associations. I think in terms of building a better performing model, I think those kind of associations needs to be removed before using the model. In terms of climate context, I think there is some evidence that this thing can be useful. This is a very recent paper this year, and as a matter of fact, just to compare new network prediction of climatologies of subgrid heat tendency in the globe. They compare two neural network simulations, one with performing this causal feature selection, one that doesn't perform this. So the idea is that if they did this, if they did the feature selection, the overall climatology agrees well with the high resolution model result. If we doesn't do that, like the climatology is all messed up. So the idea is that in this case, this sort of feature selection is very useful in order to create a better statistical models. The proposal here is that in terms of TC, such association also exists, and we need to remove that. So as a proof of concept, we've chosen 260 cases in the Western Pacific Basin, and then we use the storm tracks of those storms, and then we have some ERA5 data stored in-house. So we'll build a time series data, which contain a lot of different information. Time lag information related to the prediction and the different vertical levels, and inner core, outer core information. So the variable that we want is that we have is a normal variable, so you can find ERA5. So for example, like moisture information, like ice information, for example, vertical velocity information. So in this sense, if we do all this, we have a time series data set with like 3,000, I think 3,000 in total features. So the idea is that using this large data set, we are going to train a regression model that can provide forecasts of TC winds in the next two days. The gist here, before we do this, train this model, we perform causal feature selection, and we have another model that we didn't perform this. We perform other feature selection method like correlation analysis. So we're trying to see the difference of the performance between the two types of model that we have. This is a pretty complicated plot, so I'll go over slowly. In the y-axis, you have a correlation of a determination. So basically, if we have a higher value, it means the model is more accurate in terms of prediction. So in the x-axis, you have a number of inputs. So it means that if you have very little inputs, you mean the model is very simple. You have more inputs, meaning the model is more complex. Here you have different square points. Each square point represents one trained model. So this is the model that trained with 60 features, and this is the model that is trained with 250 features. So let's look at that model performance where we didn't do any feature selection at all. So like first 3,000 inputs, basically in terms of the validation and test set, the performance is way down there. It's not even in this plot. So it means that it's way overfitting situation going on. We're looking at those models that we have trained. We're trying to see if we add more features, it performs increasingly better to the training set, which is what we expected.
What's the MLR?
What, sorry?
MLR.
Oh, yeah.
What is that?
LSTM. Oh, multiple linear regression.
Oh.
Yeah, multiple linear regression, yeah. And if we come into the situation where we're looking towards the validation set, however, we can see that initially it starts to increase by a bit in terms of performance, but after you add more features, it's starting to drop rapidly. So it means to us that there is a region where number of inputs where we can have the best generalizing property. So it's choosing the vital information for the prediction task that we want to solve. And the summary of this is that we want to simplify statistical prediction model so that it can perform better for all tropical cyclone cases. And the causal feature selection algorithm that we have developed, like PC1 algorithm, inform us what features to keep and remove when we are creating these models. And we can see that by comparing the causality method with lag correlation method. So if we look at the lag correlation, for example, you can see that it actually performs way worse in terms of the very simple model scenario. So it means that at the very beginning, causality method is choosing the right atmospheric properties to keep while we're doing the selection process. Whereas lag correlation is probably choosing something else. So another part of the ongoing project is trying to repeat this analysis on the ship's data set. So we're working with Sarah trying to first remove some potential redundant information first. We start with 251 hurricane cases and then perform the similar things that we did before. So yeah, we see the same thing where we can have the best model with the feature selection, we just have 8 features. Comparing this to a baseline shift model with 25 features, you can see that the causal model outperforms the baseline in terms of the unseen TC cases, but not the training data set. So it's roughly similar to what we are seeing in the proof of concept experiment. One thing that might be interesting for people is that what feature is removed, what feature is retained in those models. So here we have the feature importance. Feature importance just means that how important a feature is to the prediction. So here you're seeing that in the baseline model, persistent term is very important. Like the previous time step, what's the wind speed look like is going to be very important to the prediction. Potential energy intensity, so it's like a surface flux term is also very important. I would note that there is a term, there's a combination of persistence and wind shear. It does not exist in the causal model. On the other hand, it provides extra information about how many deep convection is there in the tropical cyclone, and another formulation of the shear. So based on this type of understanding, we believe that the reason why we are seeing some difference in the performance between the two is because it removes the redundant information that we just identified, and it helps the model to generalize a little bit better to unseen PC cases. And it's an ongoing work. We are trying to use this method to also recommend some extra variable that they can use in the ship's model. So we have made some recommendations, particularly around very low level vorticity. This is one of the recommended variables. And of course, there are some mid-level moisture term as well. So it's ongoing work. They are trying to include this in their next type of analysis, just to see how it performs in their in-house models and how it looks like. So some general comment about this particular project, we are saying that machine learning, yes, it can be used to improve statistical model, usually based on removing some redundant information from existing predictor list. And it does also have the potential to enrich existing scheme by adding potential new causal driver that may work a little bit better compared to existing ones. So this is what I did with terms of causality. And the second project is my own work. It's just a paper that I just submitted to James, currently in review. So the idea is we are trying to exploit the feature detection properties of machine learning to understand a complex physical system. So this is a collaboration with James Rupert over an OU. I think pattern is very important in terms of atmospheric science. I think this is a picture from John D.J. Geier et al. In the 2019 paper. They are understanding the problem of hail generation in supercellular storms. So using this type of plot, it is very good because they can make the argument that if we have a convergence of warm and moist air into the supercell, and it can generate like larger hail. And this is based on pattern analysis. So we overlay all the pattern together and make the physical argument. And I think, at least in terms of this motivation of this work, we want to do it for like scientific experiments. So we want to identify some pattern that we can use in order to import into the Wolf model and to explain some scientific hypotheses, to create some hypotheses and test them as well. I think there's a more advanced type of task because it's very easy to do simple manipulation in the Wolf simulation, like we change the initial condition, or we can change the setting in the parameterization schemes. However, if we are dealing with pattern doing some sort of scientific experiment, it can be more complicated. First of all, how can we discover those patterns objectively? And we think that machine learning may be used to do that. At least currently, there are some methods that sort of can do that in a way. So for example, the paper I just showed as an example, it is actually using some online method, the method you can find online, to try to explain a neural network to predict the size of hail, whether or not it can produce large hail or small hail. So they will use some sort of different methods, but the gist of those methods is that you start from one particular prediction and you go back to the model and see what the input would look like to get this particular prediction. And this is the gist of explaining a neural network. Some of the method works like that. So I think that's very useful in terms of identifying new scientific knowledge. For example, in the climate domain, Levy-Barnes et al. Like have a recent paper trying to predict the sign of geopotential anomaly over at Northern Atlantic Ocean. And they try to know the relationship between this and the OLR anomaly over the maritime continent. So what they did was to train a machine model to predict this, and they used those explainable methods that we just discussed. Using this, they can find some areas that can be highlighted when the model is giving positive prediction over Northern Atlantic. Of course, other basins are highlighted with a negative prediction as well. Based on this type of plot, they can understand more about the teleconnections in the Earth system. One problematic that we identify is that this sort of method has a lot of uncertainty. There's a very recent paper comparing different methods to understand a neural network prediction. So using different methods, you can see that in terms of the sign, in terms of distribution, those are very different. So it's not good if we're trying to use them to get scientific knowledge, because if we don't know the scientific knowledge we want to get, and there's no ground truth, and there's no particular reason why we should trust the explanation of this method more than the other methods. So this sort of uncertainty I don't think is good. And the other thing is that a lot of the methods that have been used for image problems provide one explanation for one sample. So you are dealing with a lot of explanation. How do you aggregate them? And the other thing is that those explanation is multivariate, very complex, and it's difficult to assign physical meaning. Based on this, we are trying to design an interpretable meaning that we can understand what the model is doing to extract pattern explanation that is global. Global meaning that this pattern works for the entire data set that we have. So we're trying it on one meteorological problem and see how is it possible or not to do that. And I think so. This problem that we have is we have some WRF outputs from James Rupert, and it's a radiation heating field. So in the WRF simulation, there's a representation of a lot of different clouds and the radiative signature, for example, deep convection, shallow convection, and maybe stratiform as well. And however, not all information are equally important to the intensification or genesis of tropical cyclone. So the idea is to try to use some sort of method to aggregate all the useful information and remove all the unimportant information. And we will get a singular reflectivity anomaly, radiative anomaly structure that we can track with time, and then we can use it for the prediction. So in terms of scientific knowledge, one thing that's particularly useful is what does this structure tell us in terms of physically, how it relates to the distribution of clouds in a tropical cyclone. Why is it an important problem? So he has this experiment where you have cloud radiative feedback not turning on and cloud radiative turning off at certain times. So you can see that if they turn off the cloud radiative feedback, like the storm failed to intensify, there is a first order effect in the WRF simulation that he did. And considering this in the Earth, you might have some sort of relationship between cloud radiative feedback and surface intensity, and this can be considered as a known manipulation experiment, and this as a CRF equals 0 experiment. So I think the next step of this work, what we're trying to do, is to understand what sort of pattern in the radiation affects genesis the most. But it requires us to learn the full relationship and can be challenging. There is some method that we can do that currently, but they have some limitation. For example, soil radiation equation is commonly used. It requires to have like steady state and 2D thermal forcing. So if we want to understand the effect of three-dimensional heating or transient heating, it's difficult to apply this method. Another method that we can also use is the morphostatic energy variance budget. So it is an indirect measurement of TD formation because it calculates some sort of a thermodynamic term. But rather in terms of genesis, what we're probably interested in is the kinematic term, how the wind speed evolves at the surface. So they have some limitations. So what we're trying to do is to use a machine learning model to try to discover the relationship. So we start with a method. We have a very complex WRF simulation, and then we try to extract different type of anomaly field inside the WRF simulation using the EOL analysis. The idea would be if we have all the anomaly field we get from the AOF, and then we can combine them all together to create the pattern that we just discussed may be useful to track. And the idea how to do that is based on the properties of machine learning optimization. So the idea of combining them is based on the weights and biases between the input that you have, which is the field, which is the different anomaly fields of EOFs, and the ultimate prediction accuracy. So when you are training the model, you're actually telling the model, give me the best way to combine this so that the prediction is most accurate. So in this sense, if we find out this pattern, so it means that it will have some sort of stronger relationship than the prediction of the genesis than the other type of structures. So yeah. One thing that is included in the model in the final version is that we have consider a probabilistic prediction. So in terms of the prediction, we will have a probabilistic forecast, and the structure itself we will have uncertainty quantification as well. So the two are very important in getting new scientific insight. For example, in terms of the prediction, I'm comparing the prediction of the machine learning model on two ensemble members of high-end, which we use to train the model. So you can see that the original motivation is to try to explain why this particular ensemble member intensify the quicker rate than the blue members. However, if we just focus our attention to the first member, the wet member, we are seeing certain period, at least before hour 20, that the mean prediction of the neural network seems to be pretty accurate, and it has a low and a very narrow uncertainty range. On the other hand, after 20 hours, you can see that there's more uncertainty, and the mean prediction doesn't perform as well. So we believe that it has some physical meaning because we only include radiative information into the model. And in that sense, when the model performs not good and it has a lot of uncertainty, it means that extra information is needed. So in this sense, in this case, where the model is good, the interpretation will probably be coupled to radiation. On the other hand, in this period, we're probably seeing like surface flux information or latent heating information are more coupled to the interpretation. So the argument here is that we can use the uncertainty of the new network to assign physical meaning, specifically when is radiation important for a particular tropical cyclones. And we compare this with existing method. For example, here is the uncertainty of the new network. So originally it's becoming quite small and suddenly becomes large. And we compare this with the long wave term in the MSE variance budget. So you can see that initially long radiation is quite important to that particular storm before hour 20. But after that, it becomes pretty weak as compared to the surface heat flux component. So it's saying that this new network is assigning similar timing to the relevance of radiation is similar to the MSE variance budget. So it gives us some sort of trust in terms of the model is learning the right stuff, and it can tell us something about the relevance of radiation. Another thing that is very important in terms of physical understanding is those patterns that we extracted. So how can we analyze this plot so we can see that actually one of the main things that would impact the prediction is how the structure of long radiation of a particular sample is similar to the extract structure here. So in this case, almost all the sign is spatially distributed in the same location. So after the projection, you get a positive projection, which will lead to a high intensification rate. On the other hand, if this long wave structure, anomaly structure, is structured differently, very dissimilar to this extract structure, we will have a lower intensification rate. So the idea is that if a certain sample, we have the anomaly pretty close to this, you get a more intensification rate. That's the idea. So how can we learn more about physics from this? The idea would be to look at the raw field of long radiation just to see how they differ. So here we have some dipoles in long radiation. That's very important because it approximately tells us how the cloud top is going to look like. One is seeing that there's more of like a deep convective signature near the inner core, and there is a rising outflow in the inner core as well. And this is particularly true when you compare it to the slower sample. We can see that basically there's less deep convective signal and the outflow height is less than the other sample that we looked at. One thing that's quite new that we were excited about is to see this dipole signature. So it's the dipole signature of shallow clouds, which hasn't been discussed as much in the previous literature, so it excited me quite a bit. So in the fast interference sample, we can see that this shallow cloud signature is quite prominent. But in the slower sample, we can see that the signature is quite weaker than the other sample. So it's saying that by analyzing this pattern in this way, we can figure out that, okay, if we have one or more interpretation, there should be more deep convection development in the inner core, and probably there is some role that shallow cloud is playing in here as well. Finally, because the structure is three-dimensional, we can get some spatial insight that's not possible with solid liaison equation, for example. For example, if you look at the shallow convection signature that we just discussed, it is located to the southeast of the TC center, and downstream of this signature, we can find out we can see the long wave, we can see a deep convection signature. So based on this, we can say the two can have the potential to be correlated. And in terms of looking at the uncertainty of the structure, we can see that both signature, like the shallow one over here and the deep convection over here, is located in an area where the model have less uncertainty. So that means that those are probably where it's more trustworthy than the other. So in terms of looking at this structure that we just identified, we probably wouldn't trust the sign of the anomaly pattern over here, like over here, for example. So this is how we can use the model that we developed to get some scientific insight of where the radiation should distribute, where the cloud should distribute in a tropical cyclone. So this is something that we intend to use this sort of pattern that we just identified, import it back into the WRF simulation and perform perturbation experiment just to figure out the real causal relationship between this sort of pattern and interpretation of tropical cyclones. So some final take-home message. We use machine learning architecture to discover patterns from multivariate data. In this case, is WRF output of tropical cyclone simulations. And in terms of keeping the model to be simple, we can allow us to say that certain things about physics. In particular, we can identify certain period where radiation is more important than the others. Finally, uncertainty quantification is very useful because we can know that in terms of pattern where we should focus more while we're doing physical understanding, and also how it relates to the prediction itself is also can be useful if we have this sort of uncertainty quantification. Finally, I'd like to do a shameless advertisement. So another PhD student in the group, like Milton Gomez, is creating a data set for tropical cyclone studies with machine learning purposes. So a lot of things that we identify is a lot of people with a tropical meteorologic background trying to get into machine learning, but they don't know the methods or what kind of things to explain them, for example. And in the other end, you have computer scientists who will want to get into this domain, but they don't know how to process the data, they don't know how to process satellite data, model data, for example. So the idea here is to combine the two. For example, you will have a simple machine learning model with tutorial on how to use them and how to evaluate them. And also you have a process data that is good quality and also system average type of situation. So you also have some nifty visualization tools. For example, here it's plotting the vorticity evolution of Katrina, I believe. So using this sort of 3D simulations, the 3D visualization tool is available as well. So yeah, so if you have any feedbacks about this particular project, you can contact the PhD student, Milton Gomez, or my advisor, Tom Buchler, as well for details. Well, thank you very much. I'm happy to answer any questions.
Thank you, Frederick. That was a lot of information that you provided. Do we have any questions from the audience?
There are two parts to it, as I understand. One is pattern detection as a prediction.
Yeah.
So wondering about what is that time lag between those two? Okay, you are detecting something, is this an hour before, or
Sure.
how much time before you can detect this pattern to forecast a severe storm or hail size? What you're talking about?
Yeah, that depends on the specific task you want. Like sometimes you want more of a lead time, and then that also depends on what output you provide to the model, right? So if you want more of a lead time forecast, long lead time forecast, you would give the model with information about 2 days information from now, for example. In this particular example, I am targeting intensification in 24 hours. So it's 1 day intensification. Yeah, so I have tried a little bit with a shorter lead time, but the performance wasn't that good in terms of, because there's a lot of noise in the data as well. So yeah, we have skipped that and focused on more of like removing the dynamic cycle aspect. So yeah, so we're focusing on 24-hour intensification. Yeah.
Thank you. Then you showed some hail size. Is that
Yes.
you are able to predict the hail size? Is that small or big like that? Are you able to do any of those validation like that, or it's just a model?
Yeah, this is possible. I think a lot of times, in terms of this sort of analysis, need a lot of data. So you would probably use is model outputs, first of all. But of course, one thing we can do is to fine-tune those models. So for example, you have a field campaign. you receive some health size information and the surrounding information, surrounding environment information as well. So you have this trained model, right? So you also have new data source from observation. You would use that to like fine-tune the weights and biases in the model so that it performs better, like taking into account the real observation, what it looks like. Yeah, that's the idea.
Thank you.
Yeah.
Appreciate that.
Any other questions?
So if I understand correctly, your input data are from WRF primarily, which is a simulated.
Yeah.
So how do you relate it? How do you relate the machine learning nodes that you find from the numerical simulation with observation?
Yes, I think one thing that we need to do, for example, here is that, for example, in observation, you may have a satellite imagery, satellite observation. So you can also see how the cloud distributed. Maybe you can already see some anomaly in terms of how cloud is distributed. So the idea, if you have an observation, you want to validate it, one possible thing that I can think of is maybe, yeah, I can just project the overall cloud pattern, like the radiate pattern you can see from the satellite images onto this pattern. You can see roughly, is it the same distribution as what we identify here with the WRF simulation or not? And if we done this and we run through the model, and would it predict stronger interpretation or lower interpretation? So if we are saying the same thing, even with adding observational data and using this to project, then it probably means that the structure is accurate. And otherwise, we need to be more careful in terms of the analysis. Yeah.
Hi, nice talk, thank you. So the features that you're talking about, at least at the beginning of the talk, were features from WRF, right? From they are numbers or whatever. Is that correct?
In terms of the first one, maybe.
Yeah.
It can be anything. So for example, in this work, we start from the error 5 data. So these are error 5 information. Of course, it's also a model. Error 5 is also a model, but
So when you, going back a little bit, you said you tried to train it on, say, 250 features, right?
yeah.
So what are those 250 features?
Yeah, I don't have I think I might have a list here right now. So maybe I have it, maybe I haven't, but. So here I'm showing in the paper that we have shown the best model that we retain. So what are included in the final model product that we have used in analysis, right? User analysis. So a lot of times what we retain is kind of like total column ice water, for example. And there's some divergence term as well above the boundary layer. There's some upper level divergence as well. That's very important because the overall argument in that particular paper is that is retaining those convergence and divergence information, whereas in the correlation-based type of selection, it shows us like vertical velocity over a very short lead time. So the idea is retaining those longer lead time information performs better. But I don't have the exact variable list of the 250 model because it doesn't perform as well.
Sure, okay. And then just go to the image where you showed the satellite data over time, the trajectory of the cyclone.
Trajectory of cyclone. Maybe you can tell me where it is.
It was earlier. I mean, you just had it up earlier.
Yeah.
Keep going. Yeah, the actual satellite images.
Oh, these are WRF simulations.
No, the satellite images themselves.
Yeah, sure. This one?
Well, you actually had a whole sequence of them. Keep going backwards.
Okay. Yeah, I don't know where
Keep
it is.
going. Yeah. Well,
yeah,
actually
sure,
a little
sure,
bit further, maybe.
A little bit further? Okay.
Yep. Yeah, that one, say.
Okay.
So, I mean, and this is a little different from your features, but AI has been shown to have a lot of skills, say, in facial recognition.
Yes.
So how much skill does it have in cyclone recognition from a satellite image? Because surely some features could be extracted from the satellite data and fed into your model, right?
That is true. I think this is not my problem. So I think I'm aware of a lot of people who is trying to do that in terms of using like satellite imagery. For example, mostly they have actually been doing this for climate models. So because they want to do some sort of climatology study on in different like CMIP6, for example, and they want an objective threshold to identify those things. And those are mostly developed for that purpose, but I think those can perform pretty well. But in the meantime, those can be using very complex architecture, like the model architecture. So yeah, I'm not sure if you simplify a little bit in terms of better performance in terms of the validation set, how it performs overall.
Okay.
Yeah.
Okay, thank you.
All right, thanks for the talk. That was really great. While we're talking about this, so for the ship's predictors, is this trained over like the full spectrum of TC intensities, or is it? And have you looked at potential changes in what the casual model is saying is important for, say, like major hurricanes versus like,
That is
tropical
true.
storms or something like that?
I'm aware of the RI type of ships that Mark is developing, and in terms of this particular one, we haven't characterized web identification or non-web identification because we want as much sample that we can get. So we more of like general as of now, but of course it's possible. It's possible to characterize it based on removing some non-RI cases, just focusing on RI. And do the comparison that way, but I haven't done it. Yeah.
No questions online. Any further questions from the audience? So with that, let's thank our speaker.
Thanks.